All right, Wednesdays, we're pink, the 3rd of March. You guys will be able to identify and use properties of special right triangles, finishing up section 7.2. All right, we have an yes.
That's a lightish, darkish, white, not pink.
It is a pink. You are wrong. All right, so straight up, okay? An equilateral triangle, ABC. So this is an equilateral triangle. Hey, wait, did we just kind of have an equilateral triangle on problem 9 on our homework that we went over? Okay, so this is going to be a similar setup. So we know all of these side lengths are congruent. It's kind of hard to mark that last one, right? And we know all the angles are congruent, right? So what are all of these? And we also know that segment CD is an altitude. This is what we know so far. What's an altitude? Does anyone remember? We learned these different parts last time. Kaya. Okay. Not necessarily cuts in the middle. That's the median, yep. So which one's the altitude, Liam? It goes to the highest point. And what is it to the other side? Perpendicular. Because when you measure height, it has to be perpendicular to the other object. So if I'm measuring my height, I need to be perpendicular to the ground, okay? Did I tell you that my wife wants me to find a doctor? Okay, so I'm of the mindset where if I'm healthy, I don't need to go to a doctor. I go to a doctor when I'm sick, when I'm not feeling well, when I need things fixed. She's of the mindset that you need to go to the doctor every year in case something were to pop up or XYZ. So, subsequently, even though I haven't gone to the doctor in quite a few years, she wants me to... that's what she says. But, I don't think I need to. But anyway, so subsequently, I need to schedule a doctor's appointment now because my wife wants me to get a doctor's appointment, and that's what I'm going to do to make sure I'm okay. I don't even know how to do this phone call.
And you never knew about it.
What if you're like...
I don't have one. Because here's the thing. I haven't gone to like a normal doctor's appointment, except for when I had my surgery on my hip because I'm an old man. But
he's old.
I am.
Mr. Fossil.
But anyway, I haven't gone to a normal doctor just for a checkup or something like that since I was in high school. So my primary care physician, when I had to write that down on different forms, I had to go back to when I lived in Beatrice and put down him and look up the phone number and the address. I'm I don't even remember what this place is called half the time. Okay. And then so I had to do all this stuff. I'm going to pause the video now so that way people don't have to listen to this part. So we know CD is an altitude here, okay? Now, what are the measures of angles A and B here?
3. X. 2, X, yes.
We know it. We can know it. What are the measures of angle? 60. How do we know these are 60 degrees? The whole big triangle is equilateral and equiangular. So each of those are 60. So that means the angle at the top here is 60 as well, right? The big one.
You're so smart, Max.
Okay. Now, what are the measures of angle ADC and angles BDC? What are those angles?
90.
They're 90s. They're both 90 because it's an altitude, right? So they're both 90 degrees to answer that question. This was 60 degrees, okay? So what are the measures of angles ACD and angles BCD then? They're 30 degrees, right? Because they're each going to be the remainder of that 180. Because if we have 60 and 90, the other one has to be 30 to add up to 180. And the other triangle is the same setup, meaning it has to be at the same angle, right?
Sure.
So, can we say these triangles are congruent? Triangle ADC is congruent to triangle BDC?
No.
Yes.
I think we can.
But we don't know.
Angle isn't one of them, unfortunately.
Angle. Yeah. Angle.
Do we know any of the side lengths?
Oh yeah, we don't. Never mind.
So could we do angle, side, angle?
Yeah.
Okay. We could use the reflexive property and do side, angle, side. Okay. So there's a couple ways there. So we could say angle, side, angle for one of them though we talked about.
Is it a similarity?
These are just straight up congruent. Okay? Because they're literally the same angles and congruent sides, the same side lengths, okay? So, if these two triangles are congruent, is segment AD congruent to segment BD here?
Yes.
Yes, they have to be, right? Because the triangles themselves are congruent. So yes, these have to be congruent to each other. Now, if they're both congruent to each other, and this whole side is congruent to this whole side and this whole side, what does it make each of these A, D, and D to be compared to the other sides of the big triangle?
Half.
Half, right? So, if this one, let me see, find a different color here. Let's say this is X. Well, this must be X over 2, right?
Yeah.
That's whatever it is divided by 2. Does that make sense?
Yep.
Yes.
Okay. So that leads us to the first part of this 30, 60, 90 triangle theorem. Okay. So that was a really delayed theorem. Okay. This is 30, 60, 90 triangle
Why?
theorem. That's basically what I just there. Awkward. Anyway, so in a 30, 60, 90 triangle, we're going to say the hypotenuse,
HYP.
Hippo.
or HYP, is twice, because if we said here, of each of these triangles, the one we called X would be the hypotenuse, right?
Yeah.
Of the right triangle that's inside of this big triangle. Does that make sense? Okay. Compared to one of the legs. Now, of these two legs, which one has to be shorter? The one across from 30 degrees or the one across from 60 degrees? The one across from 30. So of these two legs, it's twice as long as the short leg.
What?
Does that make sense? Or no? Tracking with me?
No.
No. Like actually?
The leg is 30 degrees, and the big
So the short leg's the one that can be across from 30 degrees. Yep, because that one has to be shorter than the one across from 60 because the angle's smaller.
So what you're
So,
saying
it's
is
the one
one
angle.
of it would be
Hey guys, we have a lot of people talking at once. Gage was still talking here, okay? Go ahead, Gage.
So we're not talking about angles anymore. We're talking about sides, right?
Correct. Yep. We're talking about sides in reference to the angles. Yep.
So if I knew the side of the 30 degrees, then I would know the side of the 90 degrees. Because it's just twice the side.
Yes, exactly. In a 30, 60, 90. So our little map we did before, okay, I'm going to call this short leg. Why did I call that leg the short leg? Across from the 30. Very good. Now we know this other one's going to be the hypotenuse across from the 90 degree, right? Now let's say, let me change color here.
Green.
That this is X. Well, how do I get to the hypotenuse from the short leg then? We said we're going to multiply by 2. So it would be 2x. So how would I go back? Divide by 2. Do the other thing, right?
Question.
Yes.
Would the other one be 1.5x?
We'll actually figure that out in a bit. Kaya.
Did we already complete the rest of the blank?
No. That's why they're blank. Yep.
I'm confusing myself.
Okay.
Ignore me.
Okay, hi, confusing myself. Ignore me. Mr. Goss, nice to meet you. Okay. So, now, on these 6 problems below, I want to see what we found to either find the hypotenuse or the short leg. Okay? So, if on problem like 1, 2, 3, not 4 because we don't know anything yet, 5, and not 6 because we don't know anything yet. So, all of them but 4 and 6. If you're given the hypotenuse, I want you to find the short leg. If you're given the short leg, I want you to find the hypotenuse. Does that make sense? So go ahead and do that for all 4 of those. So on number 1, what's the length of the short leg? 6. It's half. On number 2, what's the length of the hypotenuse?
8.
8. It's double. On 3, what's the length of the hypotenuse? 10. It's double the short leg. On number 4, we don't know anything yet. Number 5, what's the length of the short leg? 50. It's half. And then we don't know anything with 6 yet. Now what I want you to do is use the Pythagorean Theorem, now that we know another side, to find the third side in triangles 1, 2, 3, and 5. Once again, using simplified radicals as your answer. Let's talk about this up here. Okay, as we work through this, what did we get for number 1 for the other leg?
6 to the radical of 3.
Okay, 6 times radical 3. 6 radical 3, 6 times the square root of 3. Any of those are good ways to say it. What did we get for number 2? 4 square root of 3. So be careful as we're saying this. I know some of us are saying to the square root of 3. That would mean like it's 4 to the square root of 3 power, which is an entirely different thing.
Well, it's an exponent,
So be careful. It's not an exponent, no.
Well, the square root is an exponent.
The square root itself is an exponent, but it's so you could say 3 to the 1/2 power, but you can't say this to the square root of this.
So I could say 4 times 3 to the 1/2 power.
Yes, yes. Although you'd want to clarify that it's not 4 times 3 quantity to the 1/2 power, because otherwise that'd be a confusing point. But that's just a very long way of saying 4 square root of 3, 4 radical 3, 4 times square root of 3. Anyway, number 3, what do we get for the other side, other leg here? 5 square root of 3. Are we noticing a pattern here, guys?
Yes, sir.
What are we noticing?
It's everything is square root of 3.
What is the square root of 3?
The shortest one is square.
You take the shortest leg, and what do you do with it?
That's square root of 3.
Multiply, not add, multiply by the square root of 3.
Like add it to the end of it.
Yep, that's the slang of it. Okay, so we're going to multiply by the square root of 3 is the mathematical operation that happens. So we've run through and simplified each one of those. That's a pattern we ended up noticing. So, going back to these other blanks we had from earlier, now we are actually going to fill these in. So, the long leg, we're going to call the one across from 60's long leg. How original. If one's called short, to call one long. Okay? It's going to be square root 3 times as long as the short leg. So if I were to do my map here, and I call this one on the left-hand side the long leg.
Do we have anything difficult coming up?
I don't know what you mean by that. Anyway, continuing on.
So I can hurt my hand.
How would we go from the short leg to the long leg, we said?
3x.
3 square root.
Multiply by
3. Point radical 3.
the radical 3, square root of 3. So we ended up getting x times the square root of 3. Whatever the short leg is, multiply by the square root of 3. How would we go back from the long leg to the short leg? Divide by the radical of 3. Now, I want you to have this written down.
Okay.
If anyone asks for questions, the first thing I'm going to do on these types of problems is says, hey, go back to your map. And this is what I mean, this is a map. Okay? I'm going to do the same thing with that 45-45-90 triangle we went over the other last class as well. If anyone asks questions on these types of problems, first thing I always say, let's go back to your map. Let's go from there. Now, not to be mean, I'm saying, hey, this is a reference point that we can use to help you, okay? I have students, every year a few students choose to draw this map and the other map, bless you, bless rains down, and let's forget, right away on their test. They get their test, the first thing they do is draw the map. And then they call it good. That way they can utilize the map the rest of the test. How this map works. Whatever you're starting with to wherever you're going. If I start with a short leg, if I'm given the short leg, I can find the other two lengths without using the Pythagorean Theorem. It's kind of handy. Now, if I'm given the hypotenuse, can I go straight from the hypotenuse to the long leg? No. Where do I have to go first?
To the short leg.
I have to go to the short leg by dividing by 2. Then I can find the long leg. Vice versa, long leg to hypotenuse can't go straight there. You have to go through short leg. If I'm giving short leg, can I find both right away?
Yeah.
Multiply 1 by 2, multiply 1 by the square root of 3. Here's another way here's a way I like to help keep this straight. Because multiply 1 by 2, 1 by the square root of 3, it gets kind of weird. Which one's which, remembering which one's which can be a little bit tough at times. Which one of these numbers is bigger, 2 or the square root of 3?
2.
2, because 2 is the square root of what number?
4.
4. And the square root of 4 is going to be bigger than the square root of 3, right?
Yeah.
Okay. So, which one's going to be bigger, the hypotenuse or the long leg? Hypotenuse. Hypotenuse is always the longest side of a right triangle. So, to me, it would make sense then that we're going to multiply by a bigger number to get to the hypotenuse than we would to get to the short leg. Does that make sense? Okay. And each of these, as you move around, is by multiplying or dividing. As you get to short to hypotenuse, smaller to bigger, it's going to multiply to get bigger. As you go back, hypotenuse to short leg, you're going to divide, because typically we associate division with getting smaller, correct? Okay?
Yeah, sometimes.
Same thing, short leg to long leg. Short to long, you're getting bigger. We normally associate that with multiplying. Long to short, smaller, we normally associate that with dividing. Okay? If you're wondering why I'm saying normally associate, it's because just because you're multiplying doesn't mean you're making the number bigger. Just because you're dividing doesn't make it smaller. There are cases where you multiply by a decimal or a negative, or divide by a decimal or a negative, where you actually end up making the number smaller or bigger, the opposite of what you would normally associate it as. Questions on that? Does everyone have this map?
Yes.
Okay.
I have a question, Joe.
Okay.
Why is math?
It's confusing when you don't understand it. When you understand it, it is awesome.
I wouldn't use them.
I would.
I'm gonna say I won't use it.
Tolerable.
Okay.
I wouldn't use that.
So on number 4 and 6, I'm going to give you guys some different lengths. And I want you guys to find the other 2 lengths.
Okay.
On 4, I'm going to give you guys this side to be 8 times the square root of 3. On 6, I'm going to give you guys this side to be 7. And I want us to find the other 2 sides in simplest radical form.
Oh gosh.
Scratch that. We're going to find these together to start, and then I'll do a couple more examples where you guys find it on your own.
Can you help my favorite?
On 4, which side are we given?
Long leg.
Long leg. How do I go? Where can I go from long leg? Saren.
To the short leg.
Short leg and short leg only. How do I go to the short leg?
Get rid of the
Divided by 3.
Divide by the square root of 3. I don't want us to think of it as getting rid of. That's going to hurt us on problems like 6. We'll see in a moment. So 8 times the square root of 3 divided by the square root of 3 is going to give us what?
8.
Just 8. Now, where can I go?
Hypotenuse.
So hypotenuse by
16.
multiplying by 2, which is 16. Did we find the other 2 lengths? Yeah, that one wasn't that bad, was it?
Nice and easy.
So we are given one side, and we found the other 2. With the Pythagorean Theorem, you have to have 2 to find the third. Special right triangles, if you know 1, you can find the other 2. Kind of cool. Questions on 4. On 6, what are we given?
7.
7.
The long leg to be 7. So what can we find?
I don't know.
A short leg.
Short leg, how?
Divided by square root.
Divided by the square root of 3. This one's going to look weird. 7 divided by the square root of 3. Do we want to leave the radical on the bottom?
No.
We say no.
1.
Multiply by 1. What is 1 going to be here?
Square root of 3.
Square root of 3 over square root of 3. On the top, you're just going to have 7 times the square root of 3. What happens on the bottom?
1.
You get normal
3.
3. Square root of 3 times itself is normal 3. Square root of 3 times square root of 3 is the square root of 9. And what is the square root of 9?
3.
3.
So,
Can we simplify 7 and 3?
21. No.
No.
21.
So the short leg is just 7 square root of 3 over 3. Doesn't look simple, but that's actually simplified, believe it or not. Now that we know the short leg, where can we go? Hypotenuse. How? Multiply by 2.
Just 7.
No, you should be the top one. You wouldn't have it at the bottom.
14.
Yeah, that's
You can just multiply the 2 and the 7. Multiply the whole thing. You doubled it.
Why do you not?
What? Why did you do anything?
Great question. Why don't we do anything with the square root of 3?
No, this.
They're multiplying together, so if you multiply one number, you end up multiplying the entire thing anyway, as well as the regular numbers multiply together. Excuse me, I'm pointing the wrong thing. The regular numbers multiply together. If this was a radical, then you multiply it with a radical.
So it would technically just be 3 over 6, which would be the same thing as the radical of 3 over 3.
I meant,
No.
What?
Over 9.
oh, because
This
it's
technically is the
normal.
square root of 9 on the bottom,
Yeah.
which is just normal 3. But when we multiply by 2, it's like a 2 over 1. So you just multiply the top of the fractions. So 2 times 7 square root of 3 is 14 square root of 3.
But why wouldn't it just be 14 times 3? Since you're...
Because we multiplied by 2, not by the square root of 3.
Okay.
Gage, does it make sense why the short leg is 7 square root of 3 over 3?
Sort of.
Okay. So here when we had 7, we divided by the square root of 3. We multiplied by 1, right?
Mm-hmm.
Multiply straight across. 7 times the square root of 3 is 7 times the square root of 3.
Mm-hmm.
Square root of 3 times square root of 3 is square root of 9, which is 3, right?
Mm-hmm.
That's how we get this.
Okay.
And then from there, we just doubled it. Does that make more sense?
Mm-hmm.
All right. Any other questions on this? Okay. I want you guys to do example 2A and B without using the Pythagorean theorem. Answers in simplest radical form. Once you have them, or have questions, raise your hand. Once you're done with these two, I'll give you guys a homework. Or excuse me, I'll say, hey, let's get to the rest of the homework. So these end up being